in this example, we're going to find the exact value of each of the following, or state that it is undefined, or DNE. You'll notice each of these questions take a trig function and use one or more inverse trig functions as inputs. You'll also may notice that the inverse trig functions and the ratios therein are not familiar ratios for the unit circle. For example, the first case we have sine of arcsecant of -4. Now, whether you're more or less familiar with arcsecant, the ratio of -4, or if we were to change this into sine of arc cosine of the reciprocal of -4, so -1/4, that still is not a ratio I know. I know things like 0, 1, 1/2, 1/√2/2, and √3/2. So I'm not very familiar with this. Thankfully, we don't need to be, because we technically don't need to solve for what angle measure arcsecant or arccosine would result in. All I really need to know is where that angle measure would be. So, what we're going to do instead is consider arcsecant as some unknown angle measure. I'll just call it A for the time being. Whatever A happens to be, as long as we can make a drawing to represent it, then all we really need to solve for is sine of A. So, all that really matters is that we know how to draw a representation for angle measure A. Now note that arcsecant has a negative input on it, and that arcsecant, or arccosine if you want to think about it that way, of -1/4, has to be an angle measure between 0 and pi. Well, it can't be between 0 and pi halves, because that's an angle measure in quadrant 1 of the unit circle, where both cosine and secant are positive. This would happen to be from -pi halves to pi, or quadrant 2. So, we will draw to represent our angle measure of A as something that would end up being in quadrant 2. And we can represent that with a right triangle down to the x-axis. Technically, this is with the reference angle. I'll call it A prime, but for sake of simplicity, I'll just work with A. Regardless, for this right triangle, I should know a couple values. You can either think about this with secant or cosine. I have cosine being the ratio of -1/4, which means I should know the ratio of adjacent over hypotenuse. I should know the adjacent for angle measure A prime, or A, is 1, and I should know the hypotenuse for this triangle is 4. It's a -1/4, and we never write the hypotenuse as negative, so that means this value, 1, has to be the negative side. Well, all we want for this now, again, I don't know the angle measure, but we just need to solve for sine of this. And all you need to know for sine is the opposite over hypotenuse, which we already know half of that. We already know the hypotenuse is 4. If we can solve for the opposite side, we should be good to go. And all that requires is the Pythagorean theorem. The Pythagorean theorem here, taking the hypotenuse squared and subtracting the adjacent side squared. So 16 minus 1 would give us the square root of 15. This ratio would end up being positive since we are in quadrant 2, where the y-coordinate, or the y-side length, should end up being a positive. So that's positive square root of 15, giving us our final answer. So, we didn't need to know what the angle measure of arcsecant of -4 is in order to solve that problem. We only need to know where to draw it. That's going to be true for the next two problems as well. The second one says cosine of 2 times arctangent of -square root of 5. Well, again, I have no idea what ratio this would result in. That's not a ratio that I know from the unit circle. Mainly because it's not 0, 1, or something involving square root of 3. So I'll just call that A for the time being and say we need to solve cosine of 2A. Well, cosine of 2A, that is a double angle identity. I should be able to rewrite that in a few different ways. It's kind of up to you which one you prefer. I personally am a fan of 2 times cosine squared of A minus 1. If you have your own preference, then you should still get the same result. I mean, you can try that if you so please. However, regardless, I just need to know what cosine of A is. If I know what cosine of A is, then I can solve this problem. And because I know tangent of A, I technically know tangent of A should equal the ratio of negative square root of 5. I should be able to draw something to represent that. So, the inverse function we're working with, arctangent. Arctangent, unlike arccosine, is not defined between 0 and pi. It is defined between negative pi halves and pi halves. Because this is a negative ratio, it can't be between 0 and pi halves. It would have to be between negative pi halves and 0. Meaning I need to draw this triangle down in quadrant 4. So our angle measure A would be a negative angle measure that results in something in quadrant 4. If I draw that as a right triangle up to the x-axis as usual, I have negative square root of 5 as my ratio, or to make it a fraction, negative square root of 5 over 1. Since tangent is opposite over adjacent, that would be square root of 5 as opposite adjacent of 1. And since we're in quadrant 2, we should know the opposite side there should be negative to represent a negative y. And like the previous question, if we can solve for the hypotenuse side here in this case, then we should be good to go. The hypotenuse side here using the Pythagorean theorem, this would be 1 squared plus negative square root of 5 squared. That'd be 1 plus 5, so this is the square root of 6. Hypotenuse is always indicated to be positive. So then, going back to my original problem, I want to solve this using 2 cosine squared minus 1. I now know what cosine is. Cosine is adjacent over hypotenuse in that triangle drawn in quadrant 4. So that's 1 over square root of 6. That will be squared and subtract 1. If you multiply through there, 1 over square root of 6 squared is just 1/6. And then times 2 will give you 1/3. 1/3 minus 1 will give you negative 2/3 as your final answer. If you solve this using one of the other double angle identities for cosine, such as 1 minus 2 sine squared instead, you should get the same result. Let's do the last problem. And for the last one, I'm going to scroll down so I have a little bit more room. We have sine of arctangent of negative 4 over 3 plus arcsecant of 3. Again, that I don't know either of those. I don't recognize the ratio of 4/3 or 3 from the unit circle. I know square root of 3, and I know square root of 3 over 3, but I don't know 3. So, this is technically some angle measure I don't know from the unit circle. This is technically another angle measure I don't know. So really what we are working with here is sine of some angle measure plus another angle measure, or sine of A plus B. That, like the previous question, should ring some bells because A plus B, that's a sum identity. I can apply the sum identity for sine, which would be sine of A times cosine of B. Because it's a plus on the inside, this will also be a plus on the outside. So plus the term cosine of A times sine of B. Which means if I can figure out sine of A, cosine of B, cosine of A, and sine of B, then I should be good to go. Then I can evaluate this. So that means this is just like the previous couple questions. Just in this case, I'm going to be drawing two triangles. One to represent A, and one to represent B. Well, A is involving arctangent, and we said earlier that arctangent is from negative pi halves to pi halves. Since that's a negative ratio, this is just going to be like the second problem. We're going to draw a triangle in quadrant 2 to represent angle measure A. Draw a right triangle to the x-axis. Tangent is opposite over adjacent, so we have 4 and 3. And because we're in quadrant 4 there, the opposite would have to be the negative side to make negative 4 over 3. We can then solve for the missing hypotenuse side using the Pythagorean theorem. However, you might not need that because you may also recognize that this is actually a 3, 4, 5 Pythagorean triple. So your hypotenuse side will end up being a value of 5. You can use the Pythagorean theorem if you do not recognize that. For arcsecant, though, which we labeled as B, that is with a positive ratio on the inside. Now, arcsecant is defined from 0 to pi, not including pi halves. So, really that means either quadrant 1 or quadrant 2 of the unit circle. Because it's a positive ratio, it's going to be in quadrant 1, which is true for all the trig functions. It's a positive ratio, it's in quadrant 1. So, B represented in quadrant 1 of the unit circle. Again, right triangle to the x-axis. Secant would be the ratio of hypotenuse over adjacent. So that means 3 would be 3 hypotenuse, 1 adjacent. And then we can solve for the opposite side there using the Pythagorean theorem. That would be hypotenuse squared minus the adjacent side squared. That gives you the square root of 8, or 2 square root of 2 if you wish to simplify. But with that in mind, we have the triangles A and B, and I have all the side lengths, so I should be able to know sine and cosine of both A and B. Sine of my triangle for A is opposite over hypotenuse, so that would be negative 4 over 5. Times cosine of B, so that would be adjacent over hypotenuse. So that's 1 over 3. We may have already known that ratio from the beginning of the problem, since we knew what secant was. Plus cosine of A. Cosine of A would be adjacent over hypotenuse, so that's 3 over 5. And then sine of B would be opposite over hypotenuse, so that's square root of 8, or 2 root 2, divided by 3. This now takes just a little bit of algebra. Multiply that through. Negative 4/5 times 1/3 gives you negative 4/15. Plus, I can simplify these next two multiplications, but I'll keep it as the same denominator to combine with the previous fraction. So I'll make this 3 square root of 8 over 15 instead of simplifying that 3 and 15. That way, I can combine this into one fraction. Negative 4 plus 3 square root of 8 all over 15. And that would be my final answer. Or I guess negative 4 plus 6 square root of 2 divided by 15 if you simplified earlier.